Welcome to the spoken tutorial on implementing proportional controller on SBHS remotely. In this tutorial, we will learn to use Ziegler-Nichols tuning method to calculate proportional controller gain, modify step test code to design a proportional controller, implement this proportional controller on SBHS, ensure that Scilab is installed on your computer, also ensure that you have internet connectivity before you begin with this tutorial. I am recording this tutorial on a Windows 7 32-bit operating system. As a prerequisite, watch the tutorial on using SBHS Virtual Labs on Windows OS. This tutorial is available on the Spoken Tutorial website. It will teach you how to do a basic step test experiment on SBHS remotely. You also need to have basic knowledge of PID tuning. You should have the step test experiment code folder available with you. You should also have the step test experiment data file with you. If not, then it is recommended that you redo the step test experiment and generate a new data file. In my machine, the data file is within the Scilab codes Windows folder, step test folder, logs folder. Here is a folder with my username and here is my data file. Let us now download the analysis code from the website. Open a web browser and go to the website sbhs.os-hardware.in. On the left hand side, click on Downloads. Download the file SBHS analysis code and save it on the desktop. Here it is. The file downloaded will be in a zip format. Right-click and extract the contents of the zip file. A folder named Scilab Codes Analysis will be created. Open this folder. Locate and open the folder Step Analysis. The Step Analysis folder will have few more folders. Copy-paste the data file generated earlier inside the kp tau order 1 folder. Double-click on the Scilab file first order. This will launch Scilab automatically and will also open the file in Scilab editor. If it doesn't open the file, click on the File menu and then on Open a File. Choose the file first order and click on Open. Locate the variable file name and change its value to the file name of your data file. I will copy paste the file name to avoid spelling mistake. Keep the .txt extension. Save and execute this Scilab code. If the data file is not corrupted and there are no errors, a plot window will open. This plot window will show two graphs. The SBHS temperature plot, which has noise, and output of the SBHS first order model, which is a smooth curve. This code basically does the job of fitting a first order transfer function using the data file. The value of time constant tau and gain kp is displayed on the top. In this tutorial, we will not use the first order transfer function. We will only use the plot of the SBHS output. Switch to the Scilab editor. Locate the line plot 2D of t, y underscore prediction. We don't want the prediction output to appear on the plot. Comment out this line by putting 2 forward slashes at the beginning of the line. Save and execute this Scilab code. Switch to the plot window. Notice that the plot window now has only the SBHS temperature plot. To save this image, click on the File menu, then choose Export to option. Give a name to the image file. I will type SBHS plot. Click on the drop-down menu for file of types and choose PNG. Choose a directory where you want to save this file. I will choose desktop and click on save. Let us open and see if the image file is created on the desktop. Here it is. Close this image window. Let me now switch to the slides. Let us calculate the value of proportional gain using Ziegler-Nichols tuning method. There are two tuning rules given by Ziegler-Nichols to calculate the PID parameters. These are reaction curve method and instability method. We will see the reaction curve method. In this method, a step input is given to the system and its output is observed over a period of time. Any practical system would respond exponentially to a step input. A tangent is drawn at a point of inflection, that is when the curve changes from convex to concave. The dead time and time constant is calculated from the time axis. This is illustrated in this figure. This is the tangent line drawn at the point of inflection. K is the gain of the system. L is the dead time and T is the time constant. Replicate this on the SBHS output figure we just saved on the desktop. I have already done this. Let me open this file. I have used Paintbrush, which is a default image editing tool on Windows. I have got the values of gain equal to 2.7, dead time equal to 1 second and time constant equal to 50 seconds. Note that these are all approximate values. The values depend on the accuracy with which you draw the tangent line at the inflection point. After you get the required values, refer to the table given by Ziegler-Nichols to calculate the value of proportional gain. For a proportional controller, we need to calculate only the value of proportional gain. In my case, the value of proportional gain comes out to be 18. Now let us see how to implement the proportional controller on SBHS. We would modify the step test code for this. Switch to the folder where you have the step test code. Here it is. Make a copy of this folder. Rename this folder as proportional and open it. Rename the step C file to proportional. Rename the steptest.sci file to proportional. Rename the steptest.xcos file to proportional. Close Scilab if already running. Double-click on the proportional.sce file. This should launch Scilab automatically and also open the file in Scilab editor. If it doesn't open the file, click on the File menu and then on Open a File. Choose the file proportional and click on Open. Change the exec command to execute proportional.sci file instead of steptest.sci file. Change the xcos command to execute the proportional.xcos file instead of steptest.xcos file. Save this file. Click on the File menu and choose Open. Select the file proportional.sci and click on Open. Change the function name from steptest to proportional. Delete the input variable heat from the proportional function input and type setPoint. In the next line, type global, leave a space and then type temp and press enter. In the next line, type ERR equal to setPoint minus temp Add semicolon at the end and press enter. In the next line, type heat equal to 18 multiplied by ERR. Add a semicolon at the end. Here 18 is the value of the proportional gain for my SBHS. You may change it according to what you would have calculated for your SBHS. Add setPoint in the input variable of the plotting function inside its function call. To do so, add a space after temp and type setPoint. Save this file. Switch to the Scilab console. Type xcos and press enter. Xcos window will open. Close the palette window. On the Xcos Untitled window, click on File menu and choose Open. Browse to the proportional directory. Select proportional.xcos and click on Open. Xcos file will open. Double-click on the label Heat Input in percentage. Delete it and type setPoint. Click once anywhere on the Xcos window to save the label. Double-click on the step input block to open its properties window. Change the initial value to 30 and final value to 40. Keep step time as 300. Click on OK. Double-click on the function block. A window will appear. Click on OK. Another window will appear. Here there is an option to enter the function name to be called by this Xcos block. Change the function name from steptest to proportional. Click on OK. Another window will open. Keep clicking on OK 3 times to finish the configuration of function block. Save the Xcos diagram and close it. Close the Xcos Untitled window as well. Switch to the web browser. On the left hand side, click on Virtual Labs. Log in with your registered username and password. Book a slot. Switch to the proportional folder. Double-click on the file Run. This will open the SBHS client application. Log in with your username and password. Make sure you are logging in at the booked slot time. Expect the message ready to execute Scilab code. Switch to the Scilab console. Type getd space / common files. Press enter. Switch to the Scilab editor. Execute the file proportional.sce. If the network is fine, then it will automatically open the Xcos window with the proportional controller Xcos diagram. Execute this Xcos diagram and expect a plot window. The plot window will have 3 plots: heat, fan, temperature. Setpoint will also be plotted in the temperature graph. Observe that the proportional controller computes the value of heat in order to achieve the setpoint value of temperature. Run this experiment long enough to observe what happens after a step change in setpoint occurs. I will now pause this recording until the experiment is executed for sufficient time. You can see that the proportional controller has responded to the change in the setpoint. You can observe that the proportional controller inherently has the property of offset. A proportional controller will always have an offset between the setpoint value and the actual value. Now let us summarize. In this tutorial, we learned to use Ziegler-Nichols tuning method to calculate proportional controller gain for SBHS. Modify step test code to design a proportional controller. Implement the designed proportional controller on SBHS. Watch the video available at the following link. It will summarize the spoken tutorial project. If you do not have good bandwidth, you can download and watch it. The Spoken Tutorial project team conducts workshops using spoken tutorials, gives certificates to those who pass an online test. For more details, please write to contact@spoken-tutorial.org. Spoken Tutorial project is a part of the Talk to a Teacher project. It is supported by the National Mission on Education through ICT, MHRD, Government of India. More information on this mission is available at http://spoken-tutorial.org/NMEICT-intro. Thanks for joining. This is Rupak Rokde from IIT Bombay signing off. Thank you.